Hey everybody, I wanted to show you the power of these kind of friction equations and the work that we've done so far. From just a tiny little bit of information, we can actually solve some really impressive problems that deal with safety and trying to figure out kind of what we need to do in order to make our cars safer or what we need to do to make our roads safer. And so I'd like to give you a scenario here of a car that's traveling kind of out in the woods at nighttime along a pretty speedy road where there isn't seeming to be a lot of traffic and everything seems to be going just fine. And all of a sudden, a deer jumps out of the woods, kind of right in front of that car, or pretty close to in front of that car, and the car has to slam on its brakes to try and stop to get out of the way, so that hopefully they won't run into the deer itself. Now, you might have heard the phrase like a deer in the headlights. They freeze, and they don't always get out of your way, and so sometimes it's really hard to stop in time. So, I want to take two pieces of information right here, which is the speed that the car is originally traveling, which right there is about 50 miles per hour, but that's 24.6 meters per second. And then the car having a mass of about 1,000 kilograms. And from those two pieces of information, just that, I'd like to go ahead and say, well, how much time does it take for the car to stop? Now, we could also calculate the distance it takes for it to stop based on those two pieces of information, but that's one additional step. So, right at the moment, I'd like to go ahead and say, well, how much time does it take for this to stop? If the driver slams on the brakes the moment that they see this deer when they're traveling that, as they're going, how much time does it take for the vehicle to actually come to a stop? And there's some important things that we need to sort out in order to make this happen. First thing you need to know is kind of what other tools do we have in our toolbox. We've got these two pieces of information, but we also have some equations to work from in order to get there. And so I'd like to write down some of these equations on the side over here in order to get there. First one is a definition of acceleration. Acceleration is equal to a change in velocity that happens over a change in time, right? This is one we've studied quite a bit over the last few weeks, making sure that we've got it. So this is our first kind of equation that we can work from. The second one is Newton's second law. Newton's second law says that if we've got a force, right, that force is equal to a mass times an acceleration. So if there's a force on an object, it will cause that object to accelerate in some way. If it is a negative force, it will cause it to slow down or travel in the negative direction. But either way, F equals ma. And this one has a second caveat to it where we can look at this in terms of a force because of gravity. Same idea here, which is known as weight, right? So this is weight. And this is equal to a mass times an acceleration due to gravity specifically. So this is kind of the weight equation in this side. We're recognizing that this G always has a particular value, right, of 9.8 meters per second, right? And this here, right, is weight. All right, so now we've got two different equations and then another form of them specifically looking at weight. We have one more equation that we have been working on now in the last couple days, and it's the idea of the definition of the coefficient of friction, which is this force of friction divided by the force normal. Now, this equation is a really nice equation. It gives us a definition of coefficient of friction, but we can also kind of rework this one too for our help as well, which shows up quite a lot, where if we wanted to figure out something like the force of friction, we can reorganize this one algebraically and say that the force of friction is equal to the coefficient of friction times the normal force. And this is going to come in handy for this problem. So we've got essentially three equations that we were working on right here. And we've got a couple alterations on those equations, just algebraically or kind of putting in this case here, a constant. All right, so this is important information that's all in our toolbox of information. And this is the given information in the beginning. And I'm just asking, how long does it take for this car to stop? Now, in order to figure this out, I actually have to go and figure out a few things along the process. One of the things I have to figure out is I need to figure out what the force of friction is. To slow it down, I need something to slow it down. So the first thing I need to figure out is I need to find out what the force of friction is. I don't know. The second thing I need to figure out is I need to figure out what my acceleration is. And my acceleration is the thing that's going to slow me down. And then that third piece of information is kind of how much time does it take for that whole thing to happen. There is one other piece that isn't here yet that might be important to us, and that's the understanding of weight. Keeping in mind that I've got this mg over here on the right, and so we're going to use that in order to help me out. Now, I'm going to avoid plugging in numbers for quite a while, and you're going to see why that's important as we work our way forward. So I'm going to start out here with the force of friction, right? So the force of friction is equal to, right, this coefficient of friction times the normal force, right? Where in this case, we've got this normal force here. Do we know what our normal force is? Well, our normal force is directly opposite whatever gravity pulls down. So if I was to look at the car here, I would say that gravity is pulling down this way. So here's the force of gravity pulling down. And the normal force is the road pushing directly up on it. So in this case, this is the normal force. Turns out that the force of gravity, right, is equal to our mass of the car times the acceleration due to gravity, which means that the normal force is directly opposite that in the same way. So I could rewrite this equation if I wanted to, and I could say that, hey, the force of friction is equal to our coefficient of friction times the mass of the car. I'm just replacing this times the acceleration due to gravity, right? Because I'm just putting Fn here in terms of the coefficient of friction and now this new kind of gravity as we go. So I've got the force of friction is just mu times the mass of the car times the acceleration due to gravity. That's kind of cool that we've got this kind of figured out. Now, if I wanted to, I could also kind of put this together and say, all right, now I know the force of friction. Now, I haven't plugged any numbers in. I could, but I'm not going to yet. I'm going to go ahead and say, well, what about acceleration? Acceleration is equal to, right, a force divided by a mass. I found that from over here, looking at the fact that force equals mass times acceleration. So if I wanted to, I could go ahead and divide by mass. And if I divide by mass, I end up with force over mass equals acceleration. Now check this out. If I was to say the force of friction is the thing that is causing the car to slow down, I can replace this F here with this force of friction that I have up above. And maybe I should have done this in a different color to not throw us off. So I could say that A is equal to the force of friction divided by the mass. And we could say, okay, let's go ahead and plug in this force of friction right here. And I'm going to do that just down below. So I'm going to say that A is equal to the coefficient of friction times the mass of the car times the acceleration due to gravity, all divided by the mass of the car. So I've just plugged in this piece in for the force of friction. Now check this out. This is pretty sweet. You'll notice that the mass of the car is on the top and the mass of the car is on the bottom, which means that those two things cancel each other out. I don't actually have to worry about the mass of the car at all to figure out what the acceleration is. That's pretty impressive. That means that any car, it doesn't matter the mass of the car, is going to slow down in the same way. It could be a tiny little Kia that has no mass at all. It could be a super tank of an SUV, but it doesn't matter. All that matters is our coefficient of friction, which is the kind of interaction between the rubber of the tires and the road, and this acceleration due to gravity. And so I can take this equation here and I can rewrite it one last time, and I can say my acceleration is equal to the coefficient of friction times the acceleration due to gravity. I suppose that's it, right? So the coefficient of friction times the acceleration due to gravity. That's it. So these two things, right, as we go, and that's your acceleration. This seems like such a simple problem. What about finding the change in time? I have an acceleration. Could I go one step further than that? Sure, I can. Let's go ahead and do that right here. So let's choose another color. And if I say that my acceleration now over here on the right is a change in velocity over a change in time, then I can go ahead and rewrite that and say that my change in time is equal to a change in velocity divided by an acceleration. And we actually have our acceleration that's down here. So that's kind of nice. I could go ahead and plug that in right up top. And if I do that, I can say my change in time is equal to whatever my change in velocity is divided by my coefficient of friction times my acceleration due to gravity. Ooh, this is getting pretty good. So all I need to know is kind of how fast I was traveling, because I was going at some speed to begin with, and I want to stop before I hit the deer. And I'm going to divide that by my coefficient of friction times gravity, and that gives me my amount of time that it takes to stop. So I actually know all the things. You'll notice that the problem has gotten significantly easier now that I've kind of recognized a few pieces. So I'm going to go ahead and plug in what I know to be able to solve this. So my change in time is going to be equal to a change in velocity. My change in velocity is I was going 24.6 and now I want to go down to 0. So my change is kind of a negative 24.6 meters per second. That's my change in velocity. It starts at 0 and it now goes down, or starts at 24.6 and it goes down to 0. My coefficient of friction is between the tires and the road. A common coefficient of friction, which I didn't give in the problem, we do need to know that as well. This is a lookupable or measurable quantity, and often between rubber and road, you end up with 0.8. So I'm going to go ahead and put that in here as 0.8, which is a common coefficient of friction between rubber and asphalt. And then my acceleration due to gravity is 9.8 meters per second every second. That's it. And if I solve this, I'm going to walk out with an amount of seconds in the end. And the amount of seconds is the amount of time that it's going to take for this to stop. Now, the other thing to note is that this 9.8 is going to be negative as well. Why? Because it's going down, which means that if I've got a negative on the top and a negative on the bottom, therefore the whole thing becomes a positive amount of time. You're not going to have a negative amount of time here. So because we're traveling downwards, that 9.8 is a negative 9.8. So let's go ahead and do that. I've got 24.6, and I'm going to divide that by 0.8 times 9.8. And of course, those negatives are going to cancel. And what I walk away with is an amount of time of 3.14 seconds. Is that a lot of time? Well, if you're trying to stop a car, you got 3.14 seconds before that car actually does stop. That's quite a bit of time. And hopefully that deer is able to get out of the way, or you're far enough away from the deer, because from the moment you slam on your brakes, you're going to be sliding for 3.14 seconds, which is quite a bit of time, and you're going to travel quite a bit of distance before we go. So this is my final answer to this question right here. It's amazing what you can do with just a little bit of information as a whole. Cool, huh? All right, we'll see you in the next one. Bye.